G'day. In the previous video, we started to look at vectors in 2 dimensions, how to add and subtract them. In this video, our focus is going to be taking that concept one step further and completing some worded problem-solving questions, specifically featuring 2-dimensional motion. So we're still looking at dot points 1.2, 1, 2, and 3, getting through this second inquiry question that asks, how is the motion of an object that changes its direction of movement on a plane described? Again, all of these content statements are about combining vectors in 2 dimensions through addition and subtraction processes. Our focus today is really getting into the analysis of those vector diagrams to actually be able to calculate resultant vectors. So our learning intentions today, first off, is to apply the skills of vector addition and subtraction that we learned about in the previous video, but actually taking them and applying it to word problems. And then from there, applying trigonometry techniques to actually solve those 2-dimensional problems. So when we are trying to solve a 2-dimensional problem, the first thing that we want to do is always draw a diagram. When we do this, we combine our vectors together in whatever way is necessary, and that enables us to draw our resultant vector, and that's going to be representative of our answer. We then want to find magnitude using trig techniques, and also find the direction with trig techniques, and also using some of the bearings concepts that we've started to learn about as well. So the question might be, when would it be appropriate to use vector addition and when would it be appropriate to use vector subtraction? I'm not going to be able to get through all of those examples in this video, especially considering that we haven't encountered all types of examples yet, but I do have 2 simple ones. First off, if I had a question like this, a person walking 20 meters north and 30 meters east, asking for their displacement from the starting point. Essentially, when we're putting displacements or vectors or velocities, combining them together and trying to find the result at the end, generally speaking, in those scenarios, we are focusing on applying addition techniques. In the second example there, it says that a boat is traveling 25 meters per second north and then changes the direction. It then travels at 20 meters per second west, being asked here to calculate the change in velocity of the boat. So for an example like this, because we're calculating change in velocity, in other words, delta V, V minus U, here we want to end up doing a vector subtraction based on the algebraic concept of finding change in velocity. So here we would take the final vector and subtract it by the initial vector. You may notice that both of these examples were in the previous video. We're now going to look at trying to solve both of these problems as examples of the application of vector addition and subtraction. So in the first question, we have 2 vectors. One is 20 meters north and the other is 30 meters east. In this question, what we're being asked to do is combine both of those displacements together to find the overall displacement of the person that is walking. That's going to mean that we are undertaking vector addition here. And to do that, we're going to employ the head to tail method. Again, what that requires us to do is draw out first vector and then draw the second vector that we're adding on. And effectively, we take the tail of the second vector and put it on the head of the first. So it should look something like that. We can then draw in our resultant vector, which goes from the tail of the first to the head of the second. So it should look something like this. And I'm going to call the resultant in this case S, simply because we are calculating a basic displacement. However, to find S, we're going to need to employ some trigonometry. So I'm going to be using Pythagoras' theorem. Now S in this case is the hypotenuse, so it's going to be on one side of the equation by itself, and that's going to be equal to a square plus b square, or 20 squared plus 30 squared. I'm also going to, as I substitute in, just square root both sides to make S not S squared the subject. So that's going to be square root of 20 square plus 30 square. And that's going to be equal to 36 meters. Please note that I am not taking significant figures into account. Technically, based on the data given in the question, the answer should be given to one significant figure. I'm not going to be taking that into account for this question. It's simply a proof of concept that we're working with at the moment. So we've got 36 meters here as our answer, but that is not the only piece of information that we need to give with the displacement. When we are calculating for a vector, we also need direction. To know what direction we're working from, we'll need this bearing here, which I'm going to label as theta. Now, theta, in this case, can be calculated using any of the sides that are present. To keep things simple, I'm going to use the 2 sides that we were given at the beginning. meaning that I'm going to need to use tan to calculate theta. Reason being that we were given the opposite and adjacent side of the triangle. TOA is the little mnemonic, is opposite divided by adjacent, so it's going to be 30 over 20. And to solve for theta, I just need to take the tan inverse of that fraction. And that is approximately going to be equal to 56 degrees. And that's just to the nearest degree. For our final answer, we need to combine the magnitude and the direction of the vector. So I'm going to write that underneath. So the displacement here is going to be 36 meters, but also we're going to include that it is 56 degrees true. An alternate bearing that we could also show is north 56 degrees east. That would also be an acceptable bearing to put down. In the second question, what we have here is that a boat is traveling 25 meters per second north and then changes direction. It then travels at 20 meters per second west. We're being asked to calculate the change in velocity of the boat. So there are two vectors that we are working with. The first is heading in the north direction, so I'm going to draw that in to begin with. And we also have a second vector which is heading to the west, so I'll draw that one in as well. So the one that's heading north, I'm going to label as u. It's our initial velocity. So u is 25 meters per second north. And our other vector, which is heading west, is going to be labeled as v, our final velocity. And that is 20 meters per second west. Now we know from previous lessons that delta v, the change in velocity, which is what we are being asked to calculate here, is always equal to v minus u. But another way that we can write that so that we can complete our vector analysis really easily is that delta v is equal to v plus negative u. What this means is we can use head to tail method to combine our u and v vectors. However, we will need to be combining not u, but instead negative u. And the way that we can show negative u is by drawing our vector in the opposite direction and labeling it as such, negative u. And these are the two vectors that we're going to combine together. So using our head to tail method, we're going to take v first. We're going to combine that with our vector negative u here, remembering to put the tail of the second vector onto the head of the first. From there, again, we can draw our resultant vector here, which is going to be going from the tail of the first vector to the head of the second. So that is our resultant. In other words, it is delta v, our change in velocity. In order to complete our vector analysis, I'm just going to label our u vector or negative u vector, and that's going to be 25 meters per second south. From here, the problem is solved in pretty much the same way as the first question. What we need to do first is find the magnitude of the resultant. And in order to do that, again, we want to use Pythagoras' theorem. So delta v is going to be equal to the square root of 25 square plus 20 square. And that's going to be equal to 32 degrees. And that's going to be equal to approximately 32 meters. Again, I'm ignoring significant figures for this answer. I'm just showing proof of concept here. Technically, the number of significant figures given should be 1 based on the data that's been provided in the question. However, we also want to calculate a bearing. And to get some more information on that, we will need to calculate the angle that is being marked here in that yellow to orange color. Again, I'm going to label this as theta, and that's something that we want to calculate next. Again, I'm just going to use the data provided in the question to begin with, meaning that we have opposite and adjacent side to theta, meaning that we're going to be working with tan here. So our TOA mnemonic is what it matches to. So tan theta is equal to opposite over adjacent, or 25 over 20. To then calculate for theta, we apply tan inverse to both sides. So theta is going to be the tan inverse of 25 over 20. And that should be equal to approximately 51 degrees. However, when we give our bearing as our answer at the end, it's not going to be 51 degrees because the angle that's being shown here is not 51 degrees from north. I'm going to draw this off to the side of our main diagram to just give a little bit more context to that. So if we have a line going straight up and down representing our north, I've then just drawn our vertex here, which features theta, which is equal to 51 degrees. Now, if we were to give a true bearing, what we could do is drop an imaginary line down here for south, and that would be our first 180 degrees. But then we would still need to calculate this second angle here, and to find that we would need to take 90 and subtract 51. And that's based on the idea that complementary angles add up to 90. That gives us an answer of 39 degrees here. So there are two ways that we can represent the bearing. First is to give a true value. So the true bearing would be 39 plus 180, and that's equal to 219 degrees true. Our other option is to give our north, south, east, west bearing. So we know that the vector is heading in the southerly direction, but it is 39 degrees to the west. So either bearing would be fine to give in our final answer. Let's put it down formally, and that is that delta V is equal to 32 meters and 219 degrees true is our bearing. That's our final answer. Again, the alternate bearing is also acceptable here as well. Thank you very much. In the next video, we're going to be looking at two-dimensional problems. However, we're going to be introducing scenarios that involve non-right angled trigonometry, meaning that we're going to need to begin to employ the cosine rule and the sine rule to be able to solve for those geometric problems. I'll see you in the next one.